Ladies and gentlemen, good morning. My name is Marco Carratù and I am a research fellow of the University of Salerno. I'm going to present a paper which would be a short description of solutions and technologies employed by the Electronic Measurement Group of the University of Salerno to provide to students the opportunity to make remote laboratory experience as close as possible to the one in presence during this COVID era. In the literature, there have been proposed numerous solutions for the realization of remote laboratory also before the pandemic emergency. We can find solution that implements more or less the same software and hardware architecture paradigms, where we can find device under test connected to a programmable measurement station controlled by a local computer that communicates with a remote host, so a remote end user. In this architecture, we can find three major players, so the instrument and the connection matrix drivers for the bus controlled by the local computer, the bridge on the data network between the remote and the local computer operating systems, and finally the human user remote computer interface. As an instruments, they can be chosen either multifunctional DAQ or standalone instruments connected by a suitable interface bus. But however, there are no standards on the market related to this kind of particular activities. For this reason, most of the solutions that can be found in literature are non-standard, or either they provide just a virtualization of instrumentation that in most of the cases are not suitable to make the right experience for the student. In this presentation, after a brief description of the UNISA measurement courses adopted for the distance learning, different solution has been presented in order to provide to the student an experience that can be as real as possible for their. Let's see now how the hardware and software has been selected for provide remote laboratories activities in our case. So the main system is made of a controller, so a workstation, connected to various measurement instruments using different buses such as the IEEE 488.2 interface, also known as GPIO-B, or using different kind of bus like the USB 3.0. The workstation is aimed to process user commands in order to gather measurement data from instruments and send them to the client when requested. In addition, a camera allows the users to see how the equipment is behaving and monitor the execution of their commands. The server is used to manage the student login credential in order to enroll the required courses. The servers so allow the students to log in into the remote lab during the assigned time slots for the guided tutorials. Furthermore, the servers allow also the student in some part of the day to train individually without the supervision of a professor or a technician. A reservation system was developed to manage all the queues that assign a priority changing in function of the previous occupancy times. This structure then has been declined in three different architectures, one for each course that will be presented now, based on the respectivity's peculiarities. The electronic measurement related courses where the remote laboratory activities were experimented were three. We can find the electronic measurements course at the bachelor degree that is a course aimed to introduce the principle of measuring electric quantities through general purpose measurement instruments. In this course, students, organized in several work groups, must make direct and indirect measurements to gain confidence with measuring instruments and the measurement methods described during theoretical lessons. Then we have the virtual instrumentation for industrial automation courses in the master's degree courses that leads students to deepen topics like digital instrumentation for analysis of circuit system and networks, and develop automatic measurement system. This kind of courses is also included in the framework of the LabVIEW Academy initiative supported by National Instruments. The third one, the last one, is the Real-Time Measurement System course in the master's degree. This course is focused on the topic of real-time measurements. In particular, during the first laboratory lessons, the students are asked to solve fundamental problems regarding the DSP peripherals, as explained during the theoretical lessons. In particular, these three courses aims bachelor students to learn the use of measurement instruments, while master students belonging to the master's degree courses should learn how to program them. Starting from the basis course of electronic measurements, here the class is made of about 80 students, collected into 20 groups of maximum 4 people. The architecture of the courses is the following. At the first, during the lesson, the professor describes the experiments and provides didactic material, like assembly diagrams, manual tools, indication, and so on. Then, the groups of students, with the supervision of professors and tutors, carry out the experiments by remote access to the laboratory previously introduced. Furthermore, in some part of the day, students are also enabled to train individually without the supervision of the tutors or professors. The management system was designed to allow more users to conduct remote experiments simultaneously. Usually, the number of experiments provided during the courses are lower than 10, that regards at least 40 hours of the total amount of courses hours. One of the first experience of this course is the use of the multimeter. For this kind of experience, each workstation is provided by a virtual bench that is an hardware made by the National Instrument, including different devices: a digital multimeter, a programmable DC power supply, a function generator, a mixed signal oscilloscope, and several digital I/O. In addition to the virtual bench, there is a virtual bench multiplexer controlled by the virtual bench digital I/O in order to switch the DC power supply and digital multimeters of the virtual bench among 3 different devices under test. In this case, the experiment aims to familiarize students with a basis instrument such as the multimeter and highlight the measurement error caused by the improper use of this kind of instrument. In particular, during this experience, the students have to program the switches, configure the instruments, and execute measurements. As an example of this experience, the students can measure the DC resistance on a dipole, the DC voltage, the DC current, the RMS voltage of a sinusoidal signal, and the multimeter frequency response analysis. The last laboratory experience reported here for the electronic measurement course is represented by the resistance measurement by the voltmeter-ammeter method. The instrument set is the following: a DC power supply of the virtual bench, the DC emitter of the virtual bench, an SP8266 based voltmeter, and the virtual bench multiplexer. In particular, the experiment is focused to see the effects of the insertion of a measurement instrument into a circuit. More in detail, the measurement is based on the definition of resistance. 2 measurements must be made: the DC voltage and the DC current. But, in our cases, the voltmeter can be inserted in 2 possible ways: the voltmeter upstream of the ammeter, the voltstream downstream of the ammeter. So, in this case, thanks to the instrumentation provided, the students can measure the values of 3 different resistors connected to the 3 operating areas of the multiplexer, and according to the student's choice, they can switch the voltmeter either upstream or downstream, and selecting the resistor of interest. In this case, the students can make the experience of the insertion of a measurement instrument into a circuit. For the master degree, the Virtual Instrumentation for Industrial Automation Laboratory aims to transfer skills necessary to design, program and characterize automatic measurement system to the students. Usually the class comprises about 30 students that are divided into groups of 4 people. Each group is assigned to a specific remote controllable measurement station, and during the laboratory hours, the students train the use of LabVIEW to generate the software to manage the automatic measurement system. For example, in our cases, in our experience, 2 automatic measurement stations programmed in remote training by the students are described together with the hardware employed. The first automatic measurement station were programmed to realize a virtual FFT analyzer using the data acquisition card provided by the virtual bench previously described. The whole software was developed by the students in the LabVIEW environment using the Workbench software. In particular, they implemented the graphical user interface, commands and queries to the DAC, and the signal processing procedures to analyze the signal in the frequency domain. The signal processing software implements also a signal translation to low frequencies. The second remote station was programmed to acquire transitory signals and convert them back into analog form. In particular, this station was provided by an oscilloscope, an arbitrary function generator, and the workstation. All of them were connected thanks to the use of the GPIO interface. In particular, the acquired samples are transferred to the workstation and then processed using filtering, noise suppression algorithm and so on, and on the basis of the user selection. After this process, the resulting signal samples can be sent to the arbitrary signal generator, which stores them and generates back the processed signal. The last remote laboratory didactic experience here presented is represented by the Real-Time Measurement System Laboratory. In this laboratory, 6 measurement stations were equipped with a suitable DSP development platform, each of them provided with AC23 stereo codecs, user-accessible LEDs and DIP switches. The 6 workstations were provided with the software code composer, which communicates with the development boards using the over USB JTAG interface, allowing the load and debug of programmed firmware. In addition, in these laboratories, 2 webcams were employed. A first one with a standard aperture allowed the students to localize their board in the field, as reported here in the picture in the left, while a second camera with a smaller aperture allows students to detect and monitor the development board LEDs. The live webcam videos are continuously streamed through a web server in order to make their videos available. In addition, the stereo audio input and output of each development board were connected to the workstation audio board. This solution have allowed students to provide signal to the DSP and listen to generated sounds with the development board. In this way, thanks to the equipment provided to the students, also from remote, they were able to complete different final course projects. In particular, here we reported 2 examples. A first project regarding the implementation of real-time dangerous road situation detection, which goal is to create real-time system that detects car crashes and sudden brakes only through audio signal processing, and a sound classification project where a real-time system was designed to set up and classify different bird songs based on their spectral continents. The pandemic disease has forced all universities worldwide to take extraordinary solutions to provide remotely lessons and laboratory activities to students. In our case, we tried to make the remote laboratory activities outcome much closer as possible to the one in presence, and avoid a missensitivity of students to real problems that could face with real instrumentation. Results and feedbacks obtained by students show a high learning level, thus confirming the goodness of choice made by the efforts. Further developments will regard the improvement of remote actuators and increase the interaction level between students and professors. Thank you for your attention. If you have any question, please write to the email here reported.